All right, I think we're recording. All right, so yeah, let's look at homework. Let me grab my textbook. All right, so problem 3.3, number 2. So construct the truth table for the following expression. Give an example, give an example, give an example. You can construct a proposition using the symbols P, Q, R. For an example, for part B, give an example other than X of a proposition generated by P, Q, and R that's equivalent to X. So yeah, write an expression involving P, Q, and R, negation, conjunction, disjunction, in parentheses. And so part A, right, is just a truth table. That's a 250 question. Part B, you're looking for an equivalent expression, something that's logically equivalent to X, other than X, right? So I mean, if you were to write down this exact thing, technically that would be, equivalent to X, but it asks for something other than that. So find something that's equivalent to this. The truth table may help you, or applying some of these laws of logic may help you, and we're gonna do an example of that in a moment also. And then part C says, give an example of a proposition that implies X. So the business here is, we don't need that stuff. We don't need that stuff. So the business here is, so find a proposition A such that A implies X, right? So certainly X implies X, that's always the case, but find some other proposition such that if this is true, you're guaranteed that X is true. So that's what part B is asking you to do. Find a proposition that implies X. I have lost my textbook. Hold on a second. All right. And then part C says find a proposition, or part D says find a proposition that is implied by X. So this is part C, and then part D, find a proposition B such that X implies B. In other words, find something such that if X is true, you're guaranteed that this is also true. And the truth table may help, but also just kind of thinking about what the proposition says, looking at X, maybe simplifying it if you can, and maybe looking at the equivalent version that you came up with for part B, right? And seeing, is there something that, if true, guarantees that that is true? Or is there something that, if that simplified version of X is true, is also guaranteed to be true? All right, and then 3.1, number 2, let's take a look at that. So 3.1, number 2 says for each of the following propositions, identify simple propositions, express the compound proposition, and determine whether it is true or false. So let me give you an example of doing something like this. So suppose we're given the proposition if it is cold or it rains, then I won't go for a run. Okay, that's a proposition. It's a declarative statement. If it's cold or it rains, then I won't go for a run. So how could we write this in terms of simpler propositional variables? Certainly we could say let P be the proposition blah, and then we could just write P. But, you know, to do these proofs, we want to break things down into smaller pieces. So I could say something like, you know, let C be the proposition it is cold. Let R be the proposition it rains. And let E be the proposition I get exercise. So we could write this in an equivalent form of if it is cold or it rains, then I won't go for a run. So if that had been a question you would ask, that would be an acceptable answer.
What about if it's just like similar form to part A, and it's just blah 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 or blah blah blah, and there's no that.
So the world is flat, or 0 is an even number. So you could set, you know, W is the proposition the world is flat. Z is the proposition 0 is an even integer, and so this proposition is just W or Z. It's just a disjunction. Propositions don't have to be in the form if-then. They often are, but that would just be, you know, one propositional variable, or, so the caret symbol, and then another propositional variable.
Can you give an example of a simple proposition? Compound proposition expressed in some one point. The compound proposition was what you just expressed in that example.
Say that last part again.
The compound proposition was what you just showed.
Yeah. So this is an example of a compound proposition, right? This is also a compound proposition. These are simpler propositions. Right, so I've written this compound one in terms of these simpler ones.
And how do you find out whether or not it's true or false? The truth table?
So the questions relate to things that we should have an answer to, perhaps, unless we play basketball. We should understand if the world is flat, and we should understand if 0 is an even integer, or if 3 is an integer and 3 is rational. So these are things that, you know, presumably we can determine the truth value of, but then we have to apply, you know, conjunction, disjunction, to put these things together. Let's see, I gotta scroll back up in chat. So that's 3.1, number 2. There's a problem that wants to show proofs for one rule. Could you prove it by choosing a value for A and B? Which problem was that was asking us to prove a rule?
I think it's 1.5.4, they said. Or section 1.5, number 4.
Oh, okay.
I think I have the same question actually for that one.
So the keyword here is verify. So when it says verify, it's not quite as strong as a proof. Okay? We want to set n equal to 3, and then we want to do something to convince the person reading this that this equation is true. Highlighting PDFs never works well. We want to convince that this sum is equal to this plus this. And this was one where I think I said think about it and try to come up with an answer. It's not sufficient to pick particulars A's and B's and show that it works in that one case. But what I'd like you to do for this problem is write out what this summation is, right? Anytime that we have something like, sum from I equals 1 to 3 of something, we can write this something, where I equals 1. We can write it again where I equals 2. We can write it again where I equals 3. And then we put plus signs in between. Okay, that's kind of our working definition of what the summation symbol means. So do that for, here's an expression, right? Set I equal to 1 and write this expression, it'll be A1 plus B1. Set I equal to 2 and write this, it'll be A2 plus B2, and so on. And then put plus signs between those and add them up. Do the same thing for this, sum of AI, do the same thing for this, and then do some algebra and see if you can show that this left side is equal to that right side. And it's not going to be incredibly formal, it's really kind of just sort of a mechanical exercise. But it's typical of something we're going to run into, which is things that feel really obvious to us. It's hard sometimes to figure out how to write those down in a logical way because it's obvious, right? So this is an opportunity to work methodically, step by step, write down what each of these three terms are in the sum, add them up, write down these three terms, add them, write down these, add them, add those two expressions together, and see if you can convince the reader that that's equal to what you got on the left. And then the same thing for part B. And that's definitely one of these play around with it and see what you come up with kind of questions. Let's see. This is good. Lots of questions. 1.5.4, good. 3.1.2. For the one where it asks if those propositions are true or false, you can just say true or false. Unless it asks for a truth table, you don't have to supply one. So yeah, determine whether it's true or false, you can just state it. 1.5.4, I just expanded all the AI and BI variables to show that they're exactly the same on either side of the equal sign. You do have to do a little bit of work. You have to use commutativity of addition, right? Which so you might have an extra line in there. And I'll level with you, that's not what I'm going to grade for points, right? But it's one that I want you to work on, and we'll talk about it in class afterwards. 3.1.2, just answer true or false. 1.5, number 10.
Nick?
Yeah.
One question on answering true or false for number 2, 3.1.2. If one part of the proposition is true and the other is false, do we go, in the case of 2A, would we evaluate the whole thing as true or false?
Correct. Yeah, you want the truth value of the entire compound proposition. And to find that truth value, you'll probably want to find the truth value of the pieces of it, right? And if one is true and one is false, and you're asked to do a disjunction, then the proposition would be true. If one is true and one is false, and you're taking the conjunction of both of them, then that would be false, right? That would be an and. But yeah, I'm looking for the truth value of the whole expression.
Okay.
Cool. All right, 1.5, number 10, part B, evaluate this thing. If it converges to 0, it's okay to say it converges to 0.
Is it okay if you say it approaches 0?
Yeah, that's okay. don't think you can do an exact number. Actually, I'm curious what that actually converges to.
Quick, someone do a calculator thing. Site, what?
That's a good question. Because at first glance, I assumed it converged to 1, but I don't think it does. Huh. I don't know what that converges to. Let me take a quick look at my calculator. Yeah, I'm gonna guess it goes to 0. Oh, product up to 100. Sorry. Yes, give an exact number for that. Sorry, I thought it was an infinite product. Do an exact number for that. And you don't have to multiply 100 things to get an exact answer. Okay, so write out the expression and try to be clever. Try to be lazy, which is often the same thing, about giving it up. Write the answer as a fraction. It'll be a lot easier. Yep, good. Zero is an even number. It's a integer times 2. Any number that can be written as twice an integer is even, and 0 can be written as twice 0, so 0 is even. And so is negative 2, and so on.
Sorry,
That's okay.
I assuming that I did this correctly, and that the calculator site is not flawed.
Mm-hmm.
It said it gave the result for the product in 10B to be 1/100th. But I don't know the accuracy of that.
It's actually going to be slightly different from that.
Great. Okay.
And try it with a top number of like 3 instead of 100, and just write it out, and you'll probably see what's going on more easily like that. And then when you do it for 100, it should match a pattern.
Okay.
Cool, excellent questions. So for truth tables, if you want to use 1, 0 instead of true, false, that's totally fine with me. As long as 1 is true and 0 is false. All right, other questions? Cool. Well, let's continue developing propositional calculus. All right, so let's go back to looking at some of these logical identities. And in your textbook, right, page 58, 59, is a good go-to. So here's these basic identities, and here's these implications, and we'll talk about implications next. But let's still just work with the level of these basic identities, commutivity, associativity, and so on. And so we talked about these last time, and you've seen these in 250 and such. So let's look at how we can use some of these things. So let me give you an example problem. And this will be a kind of dry example, but it'll get more interesting over time. So here's an example proof. Let's show the following. The negation, so P and Q are propositional variables here. So the negation of the disjunction of P with the conjunction of not P and Q is logically equivalent to the negation of P conjuncted with the negation of Q. So I want to prove this. Let's see, so back in chat, so calculator side, I don't know what site that is, but if you go up to 100, you should not end up with 1/100th, I don't believe. Try that site with 3 and see if you get the right answer. All right, so we want to prove that this is equal to that. And we have, these facts. We know that, if we have P or a Q, we could also write Q or a P, and it will be logically equivalent to the same expression. If we have P ORed with 0, that's exactly the same thing as P in terms of truth values. If P is true, then P OR 0 is true. If P is false, then P OR 0 is false. So these basic logical laws allow us to replace or rewrite one proposition with another by using these laws. Which means, for example, that that we could replace this with, something using De Morgan's theorem, for example. We could replace this with something using distribution, right? So we can certainly take one side and rewrite it in a different form. So I'm going to just play around with the left side of this. Let me give you a warning here, but we'll repeat this warning as we go through proofs in the next couple of weeks. If you want to show that something is equal to something else, right? You are allowed to pick one of these things and show that it's equal to something else, and show that that's equal to something else, and show that that's equal to something else, and eventually, hopefully, show that it's equal to exactly this thing you're trying to show. What you are not allowed to do is make changes to both sides of an expression and show that what you end up with is equal on both sides. That does not prove that this is equal to this. So let me give you a really simple example. And this will be so simple that you'll be like, well, that's a ridiculous example. I would never do that. But we'll find ourselves tempted to do this in more subtle forms. So here's an example. So bad. Example. So let's prove x plus 1 squared is equal to x minus 1 cubed. Now we know this isn't true, right? If x is any value, in general, x plus 1 squared is not going to be the same thing as x minus 1 cubed. right? I mean, I can just set x equal to 1. This would be 2 squared is 4. This would be 0 cubed is 0. So this is clearly not something I should be able to prove. But let me show you what I'll see from students typically on exams. So let m be an integer. M times x plus 1 squared equals m times x minus 1 cubed. And then maybe we'll do some fancy algebra. And then we'll say set m equal to 0, and 0 times x squared plus 2x plus 1 equals 0 times x cubed minus 3x squared plus 3x minus 1. And this is equal to 0, and this is equal to 0, and so 0 equals 0. Hey, that's true. I'm done. I proved x plus 1 squared is equal to x minus 1 cubed. Right? Well, that better not be a valid proof, because if this is true, you know, our bridges are going to start falling down and such. Let me show you an even simpler example. Prove that 1 is equal to 2. Well, I'll start off with 1 equals 2. I'll multiply both sides by 0. I'll get 0 equals 0. I know 0 is equal to 0. I'm done. I proved 1 equals 2. Okay, that's a poor proof technique and a typo. This does not prove that 1 equals 2. What you've proven is that if 1 equals 2, 0 equals 0. Right? We said if 1 equals 2, then this is true and this is true. So if this is true, then that is true. Knowing that that is true does not prove that this is true. That's the converse. The converse is not the same as the original proposition. So those are silly examples, but it's going to be tempting to do something like that. And we'll talk about it as we develop proofs, especially in mathematical induction, how to watch out for that. So what are we going to do here? We're not going to do things to both sides and then come up with, 0 equals 0 or something. We're going to start with this side, and we're going to change it into something equivalent by using these rules of logic. All right, and I'm going to write this out pretty longhand to begin with. And I want to show that this is equivalent to something using one of these rules. Now, I'm not going to skip steps, right? I'm going to try to do this by doing one thing at a time. So, let me do this. All right, so I'm trying to rewrite this expression using one of these rules. So what one of these rules might apply to this expression to let me rewrite it in a possibly simpler form, or at least a form that I can do something else with? And this is puzzle solving, right? We don't have a strictly defined set of rules we follow to do these kinds of proofs. it's a trial and error kind of thing. It's puzzle solving. It's finding something that looks like it might apply here, even if we don't see that it's going to help us down the road. It's just sort of grabbing at loose threads, right, and pulling and seeing what happens. And as we do more and more proofs, we start to develop an intuition for how to go about proving something. What should we do to an expression like this to turn it into, something else that we can work with?
What about one of the distributive laws?
Okay, distributive laws sound interesting. Distributive laws say, something ANDed with an OR can be rewritten like this, and something ORed with an AND can be rewritten like this. Well, down here, we've got something ORed with an AND. So let's go ahead and use this distribution, right, which basically says we can OR the first thing with this, and we can OR the first thing with that, and AND them together. So let's go ahead and do that. So it's still going to be a negation of whatever we make this equivalent to. So we're going to rewrite this part. And the distributive law, so I'm using the second law, says this would be equivalent to P ORed with not P, ANDed with P ORed with Q. Where this has replaced that. Everybody okay with that?
Yes.
Okay. So now I'm going to take a bit of liberty here with how I'm writing these. Well, let me do it formally the first time, and then we'll talk about legal shortcuts. Before I do this, though, I want to list a reason for everything that I write. Okay? This statement has nothing to do with the thing I'm trying to prove. This one statement by itself is a simple fact. And it's a fact because of this thing that we call the distributive law. So I'm going to put a reason over here and say the reason for this is the distributive law. And now anybody who's looking at my proof and wondering if I did things correctly has to now say, is this equivalent to that because of the distributive law? And you look at the distributive law and you should very quickly see that, yes, this is equivalent to that, right? So when we write a proof, it's not enough just to write down a bunch of steps and come up with the conclusion, right? We need to justify every step that we write. And every step that we write, except in an indirect proof, every step we write must be true. It must be true because either we know that it's true because we were told so, or because it follows from things that we already know are true. Because we've written them because we were told so, or because they followed from other things that were true. So it's this chain of true statements, right? This is essential for doing these logical proofs. Every statement you write has to be true, and you have to be able to defend why it's true. The reason this is true is something called the distributive law. Did we prove the distributive law? No, we're given that, right? So we're not going to have to go back and prove these things, right? But if we use them, we have to state that we use them. All right, so now I know that this statement is equivalent to that. I want to find something else that this statement is equivalent to. So what kind of principle could I use? What logical law could I use to write something equivalent to this that may be simpler to work with? P or not P is 1. Here we have the disjunction of P with the negation of P. And we know that's equal to 1. How do we know that's equal to 1? What's the fancy name of the law for that? Almost. The null law says p or 1 is equal to 1. Yeah, negation. I didn't mean for my cursor to be sitting right next to it, but it happened to be sitting right next to it. So that's the negation law. So negation says we can replace p or not p with 1 or with true. So this is equivalent to, I'm going to use true, ANDed with p or q. And that's negation law. All right, well, I'm going to keep going. I'm going to say the negation of t ANDed with p or q. And I want to find what that's equivalent to. So there we've got the identity law. Well, the identity law says p and true is the same thing as p. Now these variables are placeholders here, by the way, right? This just says, you know, some propositional variable ANDed with true is the same as the propositional variable. I can replace this with, you know, some proposition like p or q, for example, right? It's a placeholder. But there's one trick here. This is if we're going to be really picky, right? If I'm playing mean teacher today, the identity law says something and true is the same as something, but we don't have something and true. What we have is true and something. So being really technical, we can't apply the identity law as it's written to this expression. We really need one extra step, which is to say that this expression is logically equivalent to p or q ANDed with t. And that's commutivity. Now in practice, I won't require you to do that step, right? In practice, right, unless we want to spend our lives writing proofs, right, since the identity says p and true is the same as p, right, I would let you also say, oh, and t and p is also the same as p, right? But to be absolutely precise about it, which what we're doing right now, we need to apply commutivity to put it into this form, and then we can do our next step. And say if we take any expression and we AND it with t, we just get that original expression. And that's the identity law. So now we've shown that this is equivalent to that. So 0 is false, 1 is true, correct. So what can we do with this? And now De Morgan, there we go. So we also know that the negation of p or q is the same thing as the negation of p ANDed with the negation of q, and that's everyone's favorite De Morgan's theorem. Oh, they call it a law. I can't write De Morgan's law. It just doesn't sound right. It sounds like a bad movie. De Morgan's theorem. So what have we done now? Right? What we've done is we've applied these rules of logic and shown that this is equivalent to this, which is equivalent to that, equivalent to that, equivalent to that, equivalent to that. We've shown that this original expression is equivalent to this. Now we're also using this idea of a transitive property, right? where you know, if A is equivalent to B and B is equivalent to C, then we can say A is equivalent to C, right? We don't have to spell that out, right? And in practice, we're not going to keep writing down the left-hand side. We'd probably do this proof by saying this thing is equivalent to this because of the distributive law, which is equivalent to this through negation, which is equivalent to this through commutativity, which is equivalent to this through identity, which is equivalent to this through De Morgan's. And we wouldn't keep writing down, you know, this over here and this over here, right? But the punchline here is that we've shown that this thing is equivalent to that thing. And that's what we were asked to show. So now we can write down QED, which is Latin for which is what we were asked to demonstrate. And that's the end of our proof. Alright, and someone just asked if we have something where one proposition is not equal to the other, how would we prove that? You may be able to prove it by finding a counterexample. If I could find particular values of P and Q for which this was not the same as that, I'm done. Right? That's enough. One example is enough to show that this is not logically equivalent. The flip side of that, if we wanted to show that this is logically equivalent, if we could show for all possible values of P and Q that this is the same as that, then we'd also be done. That's what a truth table is. Right? When you can write out a truth table and see the two columns are exactly the same in all rows, that's what you've done. You've proven that these sides have the same value for all possible values of P and Q. Right? This is a different kind of thing where we're doing sort of algebraic manipulation and showing that this is the same as that. So if you studied SAR in Engineering 250, Systematic Algebraic Reduction, it's the same kind of idea. Except with SAR, there's an algorithmic way you can go about changing expressions to show one side's equal to another. But that's an algebraic approach to proving equivalence of logical expressions, right? Instead of using a truth table. That's really what this is. So yeah, to prove it's not equal, you get a truth table where there's at least one spot where the truth values differ. All right, other questions? So this is, I think, our first formal full-on proof, and we'll be doing a lot of these. And a lot of times what we're doing will be kind of a level above this, but this will be what's going on underneath. But a lot of this we don't really think in terms of, you know, not parentheses, parentheses, P or not P, close paren, blah, 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 negation law, right? But we can always come back to this and, you know, do the lowest level mechanics. How would we state that something is not equal to something else? Depending on what you mean by state, I mean, we could say right, logically equivalent with a slash through it. This means not logically equivalent. And that's probably the most common one. So you use QED when you've proven what you were asked to prove, right? It's kind of the fancy, you know, it's the mic drop basically. So if you're asked to prove, you know, that x is bigger than 7, you do all your work, you do all your work, you do all your work. Your last statement is, you know, therefore x is bigger than 7. That's where you write down QED, And it basically says, and if you look at the beginning, this is what we were trying to show, right? It's saying that's the end of the proof because we've demonstrated what we were asked to demonstrate. And don't put down QED too soon, right? Make sure that the thing right before it is the thing that you were asked to demonstrate. If you've got some statement written here from which, with a little bit of work, you can get to what you were asked to show, that's not the QED point, right? The last thing that you write should be, the demonstration of what you were after. And it's just kind of fun to write. If you don't have it, you don't lose points on it. It's not an invalid proof, but it's think of these proofs as you're going into a courtroom and you're trying to convince a judge of something, right? And so there's all kinds of procedure and protocol, at least sometimes. And so, part of that procedure is you start with facts, things that you have been told are true or things that you know are true. And then everything that you say after that has to follow from, either factual basis or things that you've just shown to be factual as part of your proof. And the goal is, if you're asked to prove blah, that you go da 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 blah, right? And somewhere at the end of the proof, you're able to say this thing that you were trying to show, and then QED is basically, I rest my case. So there's your law school thing for the day. All right, so we're going to shift gears a little bit. We're going to talk about quantifiers. So we're back in the realm of creating new propositions from old propositions. And we do this with conjunction and disjunction and all this other stuff. Another way we can create new propositions from old is by using quantifiers. And there's two quantifiers we're going to work with most. They're called the universal quantifier and the existential quantifier. So let's write these out. So the universal quantifier and the symbol we use for this is an upside down A. And it takes the following form. I'll put extra parentheses in here. We read this as follows. For all x, p of x is true. And generally we don't write is true. Right, when we write a proposition, we're usually writing it and saying that it's true by writing it down. So if I say p of x, I'm basically saying p of x is true. We can interpret this as for all x, p of x is true. And more typically, right, we might say for all x contained in some universe, p of x is true. Because the range of possible values, when we say for every possible x, for all values of x, well, we have to know what those set of possible values of x is, right? What the possible values are. So let's do some examples. For all x in the integers, x plus x is equal to 2 times x. That's a proposition. What this says is that for any integer, if I add that integer to itself, I get the same value as if I multiply that integer by 2. And this turns out to be a true proposition. For all x in the integers, x plus 1 is bigger than x. True or false?
False.
So if it's
there's negative, right?
well, so if x was negative 10, x plus 1 would be negative 9, which is still bigger than negative 10.
Oh yeah. Fair.
Yeah, so negatives are funny that way. So this turns out to be true. For all x, x squared is bigger than or equal to 0. True. Why is it true?
Because for all negative and positive integers, it's greater than 0, and for 0 itself, it's equal to 0.
Yeah, 0 squared is 0. Negative squared are always positive, right? So this is true if we're talking about integers, and it's true if we're talking about reals. But if we were talking about complex numbers, this becomes false. Because I, which is the square root of negative 1, I squared is negative 1, that's not bigger than 0. But if it's in the reals, this is true. So the universe of discourse, right, the set over which we're working, can definitely affect the truth of this proposition. I don't know if I doubt I just made it up, but I don't know if it's really the right term. But I think that's called the universe of discourse. That's like some ancient memory that just got dusted off in my brain. Right, and then there's I, cool. All right, so you got the idea, right? So you got to specify the set that you're working over. All right, our other quantifier is the existential quantifier. So the existential quantifier is written as a backwards E. And we read this as there exists an X such that P of X again is true. There exists an X such that P of X is true. So over whatever universe we're working on, this statement says there's at least one value of X which makes this proposition true. So there exists an X in the set of integers such that X equals 2X. That's true. In particular, the value X equals 0. There exists an X in the set of positive integers such that X equals 2X. That's false. Any positive integer, if you multiply by 2, you get a different number from the integer. All right, so universal quantifiers for all existential quantifier is there exists. And they're kind of opposite ends of a spectrum, right? This is saying for every single x, this is true. So any x you can think of in the universe, this has got to be a true proposition. This says there's at least one. There's not 0 x's, but there's at least one x. If there's only one x, this is still a true proposition. It only requires one. Universal quantifier requires that every x makes that proposition true. And we can combine these. So we can put these together in all kinds of interesting ways. For example, there exists an x. So let me just work over the integers. So I won't list my universe inside here for a moment. I'll just assume we're always working over the integers. So there exists an x such that there exists a y such that x plus y equals 0. Well, what does that mean? Break it up into pieces. This piece right here says there exists a y such that x plus y is equal to 0. Well, we don't know what x is, right? But I'm going to write this as a proposition p of x. I'm going to say let p of x be the proposition. There exists a y such that x plus y is equal to 0. It's a proposition about x. If I said x equal to 5, p of 5 is the proposition that there exists a y such that 5 plus y is equal to 0. If I said x equal to negative 10, p of negative 10 is the proposition that there exists a y such that negative 10 plus y is equal to 0. So this is a family of propositions in an unknown propositional variable x. So let's think about p of 1. P of 1 is the proposition there exists a y such that, I'm going to rewrite this a little, y plus 1 is equal to 0. P of 2 says there exists a y such that y plus 2 is equal to 0. P of negative 10 says there exists a y such that y minus 10 is equal to 0. So let's just look at these three examples. Is P of 1 true or false?
True.
That's true. P of 2 is also true. P of negative 10 is also true. It looks like P of x is always true. But this just simply says there exists an x such that P of x is true. We could have stopped right here. Right? If we just let x equal to 1, this inner proposition is the proposition that there exists a y such that y plus 1 is equal to 0. And that's true. We can pick y equal to negative 1. So this is absolutely positively true.
Will it still be true if you remove the restriction of all integers? Just have it be all values in the universe?
So it depends what your universe is, but I think if you do this over the positives, yeah, I think it'll still be true.
What about complex numbers?
It's definitely true over complexes. I'm not sure it's true over positives. Yeah, it may not be true over positives even. So P of 1 would say there exists a y such that y plus 1 equals 0. Well, that's false. Because the only y that satisfies this is negative 1, which isn't in the set of positives. P of 2 would say there's a y that you can add 2 and get 0. That's false. So I think this fails over the positive integers. But if we work over the set of all integers, it looks like for any x we think of, this inner proposition is true. So we could actually write something much stronger, which is for all x, there exists a y such that x plus y is equal to 0. And it seems like that's true. Because for any x that we pick, right, p of x is satisfied by letting y be equal to negative x. On the other hand, if we switch these around, there exists a y such that for all x, x plus y is equal to 0. What do we think about that?
Say that again.
So this expression right here, there exists a y such that for all x, x plus y is equal to 0. So if we write this middle part as p of y, it's a proposition in the unknown variable y. This is the proposition that for all x, x plus y is equal to 0. So let's just look at a few values. What does p of 1 say? P of 1 says for all x, x plus 1 is equal to 0. Well, that's clearly false, right? It's not true that for all x, x plus 1 is equal to 0. If I said x equal to 5, 5 plus 1 is not 0. So p of 1 is false. P of 2 says for all x, x plus 2 is equal to 0. Well, again, you know, if x is 5, this is not true. So it's not true for all x. If I try p of a negative value, this says for all x, x minus 5 is equal to 0. Well, that's only true for one x. X happens to be 5. If x is equal to 6, this is not true. So that's false. And we could try, you know, good old 0. P of 0 says for all x, well, it basically says x equals 0. And that's not true. And if we think about this, we'll find that no matter what value of y we pick, p of y fails to be true. Well, this proposition says that there is at least one y for which this is true, but it looks like for every y this is false. And so this proposition turns out to be false. So you can always come back to words to think about this, right? And the moral of this part of the story is really that the symbology can lead you astray, right? If we start to get kind of loosey-goosey with these things, we can introduce things that aren't logical. Like we might think that swapping the order of these isn't going to change the value of anything, but it really does. So come back to these. We won't do too much with nested propositions, but it's a good example, right? Come back to breaking this down as like for all x something, and just analyze that something. Play around with that. Think about it, right? And once you understand what that proposition is saying, right? It's a proposition dependent on x. Now say, is that proposition true for all values of x, or does there exist a y where this proposition of y is true? But mostly, right, don't be lulled into trying to do traditional symbolic manipulations that we're used to, because they might not work in this case. Right? These are sometimes strange creatures. So we can look at what some of these quantifiers are equivalent to. And for example, if we say for all x, p of x, well, this is saying, you know, for any x that you think of, this proposition is true. Any x you think of, I'm thinking of the number 15, I'm thinking of a purple cow, I'm thinking of a fountain pen, right? Whatever the universe of discourse is, for any x I pick in there, p of x has got to be true. Well, what is the opposite of that notion? This notion says for any x, p of x is true. What would be the opposite case, in some sense?
The same statement but negated.
So we could negate this. There's no such x. There's no x such that p is true. Almost. So this is saying for all x, p is true. If that's not the case, we don't know that for all x, p of x is false. Right? So this says, you know, for all politicians x is honest, right? Well, if that's not the case, we don't necessarily know that all politicians are dishonest, but what do we know?
That some of them aren't honest.
Yeah, we know that there's at least one politician that's dishonest, right? If all politicians are honest, right, that's what this statement says. If this fails to be true, there's got to be at least one x for which p fails. So this is the same thing as there exists an x such that not p of x. So the negation of the universal quantifier is really the existential quantifier applied to the negation of your proposition. And that can be a fun one to kind of think about in terms of getting comfortable with these quantifiers. So for all x this is true, there is at least one x for which this is false. This says there's at least one x for which this is true. The negation of that would be, you know, well, if there's not at least one x for which this is true, then for all x, this must be false. So those are logically equivalent. That is weird. We're going to make it weirder now. Suppose we have a family of propositions. So, like this. So suppose we have propositions P of 1, P of 2, P of 3, and so on. So for any positive integer I, we have some proposition P of I. And suppose I write the following. So for all I bigger than 0, P of I. Right, so here my universe of discourse is the positive integers, and over here I've written this proposition for all positive integers I, P of I is true. Well, this is logically exactly the same thing as the following. Saying, you know, well, if this is true for all I bigger than 0, it must be true for I equals 1. So P of 1 must be true. And this is also true if I equals 2, because 2 is bigger than 0. So P of 2 is also true. And if I equals 3, P of I must also be true, so P of 3, and etc. So this statement over here, for all I bigger than 0, P of I, is the same thing as writing the conjunction of all of these P sub i's. 1, 2, 3, 4, and so on. So it's a big, long AND statement. Right? Get out your infinite input AND gate and connect all of these to the inputs. And this is the output. On the other hand, what is this equivalent to in the same kind of spirit as the previous line? What could we find as an equivalent expression for there exists an I such that P of I? So someone said it in chat. Same thing but with or, right? This says that, you know, for at least one value of I, P of I is true, which means that, you know, maybe P of 1 is true, or P of 2, or P of 3, or P of 4, or, but somewhere there's got to be at least one I for which P of I is true. That's what this says. So the universal quantifier somehow tied into conjunction to AND gates, and the existential quantifier somehow tied into disjunction or OR gates. And that's kind of cool, if you're into that kind of thing.
Are there any quantifiers that tie into exclusive or no?
I think you could cobble one together. Oh, yes. Yeah, thank you. So if we put an exclamation mark after the existential quantifier, that says there exists a unique x such that P of x. And for two variables, that's our exclusive OR. It would say P of 1 or P of 2, but not both. But XORs don't work like that for more than two variables.
What's the significance of the exclamation mark? Since we already have another mark for negation, what's that?
It's not a negation. It says a unique x. So this this says there exists an x. This says there exists a unique x. So this, you need at least one x that makes this true, but you could have two x's, you could have five x's, you could have every x, and this will still be true. This says that there is a single x for which this is true, and for all other x's, P of x is false. So there exists a unique. So it's just tagged with an E with an exclamation mark next to it. And it's really just a compound symbol. It's not really an operation. So that's a little exclusive ORI, but not exactly. So there can only be one x, right? Let's see. There can only be one.
One exclamation point after?
It's not an operator. It's not a negation symbol. This is a different symbol. Think of it like that, right? It's just a different symbol that happens to be composed of two pen strokes with a space in between them. But this thing is called, you know, I don't know what it's called, but it's the unique existential quantifier. It would be like a function name in C that had a space in it. It would be really confusing. But that's what we got. So it's saying there exists a unique X. Does that make sense? Or do you get what I'm saying? I'm not going to ask if it makes sense. So it's a little unfortunate symbology. All right. So we've got universal quantifiers. We've got existential quantifiers. We sometimes can nest these things, and it's not always intuitive what happens when we nest them and we swap them around. Let's see. All right, I think that's as far as we needed to get today, which is good because we are just about out of time. So we've got proofs. We've got quantifiers. All right. So Friday, turn in your homework. Come to office hours if you have questions on that before then. And Friday we will start going through using these rules of inference, right, page 59 in the text, to start doing some very formal proofs. And we'll do that for a couple of days, and we'll talk about fallacies. We'll prove some interesting things, and then we're going to go on and switch gears again and talk about some number theory. And then we'll come back to proofs a week after that. All right, enjoy the afternoon. I will see you next time.